Welcome everybody to the course on the geometric anatomy of theoretical physics. And you being advanced students, you know that theoretical physics is all about casting our concepts about the real world into rigorous mathematical form, for better or worse. But theoretical physics doesn't do that for its own sake, but it does so in order to fully explore the implications of what our concepts about the real world are. So to a certain extent, the spirit of theoretical physics can be cast into the words of Wittgenstein, who said, "What we cannot speak about clearly, that we must pass over in silence." Well, so indeed, if we have concepts about the real world and it's not possible to cast them into precise mathematical form, that usually is an indicator that some aspects of these concepts have not been well understood. So theoretical physics aims at casting these concepts into mathematical language. But then mathematics is just that. It's just a language. And if we want to extract physical conclusions from this formulation, we must interpret the language. And that's not the purpose or the task of mathematics, that's the task of physicists. And that is where it gets difficult again. But again, mathematics is just a language. And to again use Wittgenstein, he says, the theorems of mathematics all say the same, namely nothing. Okay? And so what does he mean by that? Well, obviously, he doesn't mean that mathematics is useless. He just refers to the fact that if we have a theorem of the type A, if and only if B, A and B being propositions, then obviously B says nothing else than A does. And A says nothing else than B does. It's a tautology. Okay? Now, of course, mathematically, logically, it's a tautology. But psychologically, or for our understanding of A, it may be very useful to have a reformulation of A in terms of B, right? So with this understanding that the mathematics just gives us a language for what we want to do, the idea of this course is to provide proper language for theoretical physics, and certainly for the 4 courses you have heard so far. So the aims of the course, or the aim, the overarching aim, is to provide proper mathematical language for classical mechanics, electromagnetism, quantum mechanics, and statistical physics. Now, so these subjects you studied in the modules TP1 to TP4 here at Erlangen or at many other universities. And obviously, we're not going to revise all the mathematics that are needed for these 4 subjects, but rather we will develop mathematics from a higher point of view that we can now approach, that you have some prior knowledge of these subjects. And so far, you have certainly used a fair amount of analysis in order to study these subjects. Further, a fair amount of algebra, mainly linear algebra, but also nonlinear algebra at times, and geometry in one or the other form. So very often in classical mechanics, you would appeal to geometric intuition in setting up a problem or finding the solution to a problem. The same goes for electromagnetism. Algebra you mainly used in quantum mechanics. That's the modern way to do quantum mechanics, is by means of linear algebra. And in statistical physics, you use some geometry, maybe without really realizing it, by looking at convex cones of states and so on. Now, if you take these four fields and you try to be pedagogic about it, you draw circles around them. And so classical mechanics and electrodynamics certainly use a fair amount of analysis and geometry, and so does general relativity for those of you who took that course or about to take it. Well, quantum mechanics lies certainly well in the intersection of analysis and algebra, usually called functional analysis. And, well, algebra and geometry, let's do statistical physics justice, it more or less lies there. Of course, this is not a pure picture. This is mainly where the intersections of these fields come to play. And here in the middle, where these three fields intersect, we have differential geometry as a mathematical subject. And it's differential geometry that this course is mainly about. So the mathematics of this course will be that part of the mathematics of these different theoretical subjects where these three fields intersect. That's the rough idea of this course. Now, the structure of this course and indeed the development of differential geometry that we're about to start starts, well, with sets. So we'll talk about set theory, because any space in classical mechanics, the space of configurations or the phase space, in electromagnetism, the space on which you work, or in quantum mechanics, the physical space over which you construct your Hilbert space, and so on. All these spaces are certainly sets of points. That's the coarsest structure of such a space. It is a set. But what precisely is a set? Well, one can delude oneself into thinking one understands a set by saying a set is a collection of elements. But that just raises the question what a collection is and what elements are. So we certainly need to do better, and there is a fundamental problem if we start writing a book about mathematics whose pages are all empty yet. Because what could the first definition be? For a definition, you need notions that you already have in order to define a new notion. But if you don't have any notion yet, how do you start? Well, the trick is to start axiomatically, and so we'll have to write down axiomatic set theory. But that then raises the question, in what language would you possibly do that? So actually, before we come to set theory, we need another building block down here, and that will be logic. And we will deal with propositional and predicate logic first. That will define our language, and then we'll be able to write down the axioms of set theory. Now, once we have the axioms of set theory and we have our beautiful sets, the question is, what can we do with them? And one thing we certainly need, at least for these four subjects, we need a notion of continuity. For instance, in classical mechanics, famously, particles don't jump. So the particle trajectory doesn't stop somewhere and start somewhere else again. It's continuous. So you need a notion of continuity. And such a notion you get by distinguishing certain subsets of the basic set you have. And that leads to the notion of topology. So we'll deal with topological spaces and all the notions associated with that. Now, there is an abundance of topological spaces, such an abundance that you cannot even classify them. And so we will need to restrict somewhat to interesting topological spaces. Well, topologists may disagree that only those I'm going to write down are the interesting ones, but from the point of view of theoretical physics, immediately interesting are the topological manifolds. Topological manifolds, which we're going to define, are topological spaces that locally, around a point, look like some r to the d. Now, that's not enough. If you have topological manifolds, you also need, in physics, especially in classical physics, you need a notion of derivative. You need to be able to talk about the velocity of a curve. And that cannot be done in topological manifolds. What you need there, you need differentiable manifolds. And that's an entirely new beast. And there we will need to introduce the technology of charts. And the technology of charts will, for the first time, make contact to much of the formalism you already used in the standard courses. In fact, all the standard courses have been formulated in charts so far. I'll explain later. A chart is like a sailor uses a chart of the world. You travel across the globe, and if you want to know where you are and where you want to sail, you take out your atlas. In the atlas, you turn the pages, and you find the appropriate chart around a point where you are in the real world, and you can navigate in the chart. And the chart should be a one-to-one picture of the world locally, because if you then move in the world such that in the chart you would leave the page, you better turn the page and you find the other page that slightly overlaps with the chart in the atlas, so that you can then navigate on with the other chart. And very much the same thing, looking for another chart that overlaps and understanding how the overlap works. That's the whole philosophy behind manifolds, and certainly behind differentiable manifolds, because differentiation, the charts are parts of RD, like R2 for instance, and so you understand differentiation in the charts, and we will lift the notion of differentiation that we understand well in the charts, we'll lift it to the general concept of differentiation on the manifold. That's already the entire philosophy.
Well, that's a difference between a chart and a map, but it's probably roughly the same, right?
It's roughly the same. Chart is the technical term in this case.
Okay.
That's right. Okay, so we'll certainly come to that. Now, once we have differentiable manifolds, maybe already before, we'll come to a notion which, well, in some sense is yet another structure, but it's bundles. So the idea of bundles is you take a manifold and you take another manifold, and to each point of a given manifold you attach the other manifold. You build a bundle. You could have a vector bundle where to each point you attach the tangent space and so on. And bundles are a very important concept in geometry, in differential geometry, and indeed much of modern physics can be understood or can be cast into the language of bundles. So this is true for particle physics, but also for gravity and so on, certainly for quantum mechanics. So actually about already here, we will learn that a notion of position vector should be forbidden. There is no such thing as a position vector. Doesn't matter how often it's repeated, there is no such notion. Now, in bundles you learn there is no such thing as a wave function in quantum mechanics. You get away with the notion of position vector unless you look too closely, and then it fails. And the same is true in quantum mechanics. You get away with the notion of wave function, but then it fails. In fact, a wave function is, a position vector is just a collection of coordinates, but they do not constitute a vector. And the wave function in quantum mechanics is not a function at all. It's a section in a complex line bundle over the physical space. You cannot understand this, but you will at the end of the course. So these notions are needed if you really want to say what's going on. Now, okay, so once we have bundles, or maybe also alternative to bundles sometimes, so don't take the picture too seriously. It's a rough idea of how this building is constructed. We'll have geometry. Geometry comes in form of so-called tensor fields on this structure. So that could be symplectic geometry. That would be the geometry of classical phase space in mechanics, but actually it's a much bigger subject because for virtually all dynamical systems of interest to us, the phase space is equipped with the symplectic geometry. There may be a metric geometry. This is certainly the case in electromagnetism. You, to a certain extent, need a geometry, you just need a volume form. And certainly it's the case in relativity, and especially in general relativity, you need a so-called Lorentzian metric. This is a structure that sits on top here, but you need to understand more or less all of this in order to really professionally deal with geometry. Well, and then to complete this, then what I promised you, that all these different subjects you learned about before, so up to here, it's just mathematics, but then up here, it's physics. So you have classical mechanics, electromagnetism, quantum mechanics, statistical physics, and special relativity and general relativity, all of these physics can be understood and can be properly understood by mastering all these mathematics. And again, the purpose of this course is to develop these mathematics and then to show, mainly by examples, of how the insights you gain from here play out at the level of physics. That's the idea of this course. Are there any questions so far? Okay, so let's start with logic. So chapter 1 is actually already axiomatic set theory. In the first section here, yes?
This was really the question. Where's the logic behind this? You said the logic comes first before the set theory.
Yes, and the logic behind the logic is that now the first subsection will be propositional logic. Okay. So I summarized the logic under axiomatic set theory because it's the language for axiomatic set theory. So 1.1 is propositional logic. Now, the key notion of propositional logic is a proposition. Definition: a proposition P, small p, is, well, let's call it a variable, whatever that means. It's a variable that can take the values true or false. And no others. That's it. That's a proposition from the point of view of propositional logic. So in particular, it is not the task of propositional logic to decide whether a complex statement of the form "there is extraterrestrial life" is true or not. That's not the task of propositional logic. Propositional logic already deals with the complete proposition, and it just assumes it's either true or false. You can say, well, let this proposition have the value true. Yeah, you can do that. But if nothing is said, it's either one, not true at the same time, of course, no other, it's true or false. You know this. It's also not the task of propositional logic to decide whether a complex proposition of the type in winter it's colder than outside, well, this is a proposition at all. Well, obviously the one I just mentioned doesn't seem particularly reasonable, but it's not the task of propositional logic to decide this. It's important to realize this. Okay. Propositional logic deals as its atomic, elementary notion with the notion of propositions. Now, certainly you can build new propositions from old ones. Or from given ones. And one does so with the help of logical operators. And they come in different forms, and the simplest form is unary operators. And there are 4 unary operators. What's a unary operator? A unary operator takes one proposition, P, and makes from it a new proposition. So the one that's hidden in the unary means you take one proposition as given, you construct new ones, and of course this one proposition can have values true or false. Now, I said there are 4 unary operators. Let's write them down. Well, a famous one is the not operation, not P. Not P is, again, a new proposition. A proposition called not P. And this proposition, if P takes the value true, this proposition takes the value false, and if P is false, this proposition takes the value true. That's one of them, and you certainly saw this before. Well, there are 3 others. There's the identity, let's call it id P. This is true, false. There is something like we might call the tautology operator TP. This is always true, independent of what P is. And there is this operator, let's put it upside down, P, that's the contradiction, that's false, whatever P is. And you quickly check that if P can be true or false, these 4 are all the possibilities you have for defining a unary operator. Well, the next step are binary operators. In order to see how many of those we have, well, you need to start with 2 propositions that you assume are given, and they can take the values true, 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 false, false, true, and false, false. And so the easy one, certainly known to all of you, is the AND, P and Q. And P and Q is a new proposition, so this in total is one new proposition. This is true, false, 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 in the cases where this is true and this is true, and so on. Now, there are a whole number of others, and you can quickly calculate if for these 4 rows, you can in each row decide whether you put a true or a false. You have 2 to the 4 equals 16 binary operators. Yes?
So just to make sure, we are talking about operators as objects that translate one proposition into another one, but not to the construction of a proposition and the operator, and the thing in between.
That's right. So a unary operator takes one proposition and constructs from it a new proposition.
So we're not writing down the operators, but rather what an operator makes to a certain proposition.
Yes, but that's the notion of an operator. It takes 2 variables from this set. So it goes, if you would say, from the Cartesian product of the set true-false with the set true-false to the set true-false. It's a map. However, I'm not saying it this way because we don't know yet what a set is. We don't know yet what a Cartesian product is. This is an elementary presentation of this. One can do this even more abstractly and just write down deduction rules. Never write down such a table and you write down deduction rules. This is the even more abstract way of doing this. I didn't choose it because it has no purpose whatsoever if you do standard logic. If you do non-standard logic, like intuitionist logic, then you reduce certain deduction rules, and then you get a logic that you can no longer express with these tables. Okay? And, well, that is very esoteric. I don't say it's not interesting. I find it very interesting, but every course has to define its bottom line. And so this course defines the bottom line at not writing down propositional logic using deduction rules and axioms, but rather presenting the tables, because it's really sufficient for what we're going to do. Okay. Okay. So now there are a number of others. There is the OR, there is the exclusive OR, and so on. So the P or Q, you know this is true, 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 false. The exclusive OR is false, true, true, false, and so on. So in medieval ages, people were discussing whether the OR that appears in some sentence actually means the inclusive or the exclusive or, and obviously they appealed to the Bible in order to see how God used it. It was actually, again, Wittgenstein and Frege and others who, more or less around the turn of the century to the 20th century, said, no, hang on, it's just a table, it's just a definition. You have 16 binary operators, each of them maybe deserve their name or not. You have 16 of them, you have the inclusive or, you have the exclusive or, and so on. Now this is all child's play, and you've seen this before. But I go to such length in writing this down because there is one binary operator which sometimes is a little ill understood unless you're maybe very knowledgeable about these things, and that's this implication arrow. So from school days, we use this implication arrow as saying, I write down something that's true, and now I do something valid, and then I may write down this implication arrow, and that means I did something okay. Now, the implication arrow, as much as the and, is a binary operator that takes a proposition and another proposition and makes one new proposition out of it. So this whole thing, P implies Q, is in total true or false. When is it true and when is it false? From true follows true, this is evaluated to be true. From true follows false, no, mistake, you don't pass the test. From false follows true, you say no. Well, yes, you should write a T here, that's at least the definition. And from false follows false, well, that must be certainly a wrong conclusion. No, it is not. It's also true. Now, this is the definition of the implication arrow, and this is why I go to such great length about this. Well, this principle that from a false assumption, you can conclude anything, and the whole thing is evaluated to be true, deserves a name which this principle has been in place for a long time. So the principle is called, in Latin, ex falso quod libet. Roughly translated, it means from a false assumption, you can conclude whatever you like. Ex falso quod libet. And these first two, they're kind of intuitive. Now the question is, why on earth would you define the implication arrow like this? And the answer is hidden in a little theorem, which is very simply proven. The theorem is P implies Q. This statement, so I put it in brackets, is actually equivalent to, now this equivalence arrow we haven't defined. I define it here on the left-hand side. P equivalent Q is true if both are true, false if one of them is not and the other is, and true again if both are false. P implies Q is an equivalent statement to, now careful, not Q implies not P. So the order, if you put the not in front, the order is exchanged. And because I didn't tell you about the binding strength yet, you may be careful and put brackets around here. Now, this looks funny. It's quickly proven. We'll do it in a second. But the important thing about this logical mumble jumble is the corollary. This actually means we can prove assertions by way of contradiction. So assume we know that P is true, or it's the assumption that P is true, and we want to prove that then Q is true. What we can do instead, which is fully equivalent, is to assume that what we want to prove is not true, and to prove that that means that the assumption isn't true. And we say, oh, contradiction, so Q must have been true. Well, this is what this says. So this statement says you can prove assertions by way of contradiction. It's a very elementary principle, a very sharp tool of mathematics. Now coming back to your question about these tables and what map this is, such an operator, if you formulated logic in terms of these deduction rules and axioms without the tables, you could surgically remove certain deduction rules. And one of them that you can remove, such that the whole thing cannot be written down by tables anymore, would be one that destroys this theorem. And then you would have a logic, and build on it, you would have a type of mathematics where proofs by contradiction are no longer allowed. You'll probably, in every good mathematics department, you find one professor who follows that kind of, I think they call it intuitionist logic. And it's a pain because the course takes double as long as usual, because you have to constructively prove everything you want to prove. And some people make a strong point that that is very meaningful. It's certainly a better result if you know something constructively, but they make an even deeper point. They say, we do not trust the proofs by contradiction. Anyway, we're not going into that. With our definition, we have logic that allows proofs by contradiction, essentially by this definition. Well, so how do you prove such a thing? Well, this is important for the first vanilla problem in any exam. Well, of course, you use the tables and you construct this. So you have P, Q, you construct not P and not Q. So true, 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 false, false, true, false, 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 true, true, false, true, false, true. And then you write down P implies Q. And you know this from before, it's true, false, true, true. You write down not Q implies not P. Well, you construct it from here. False implies false is true. True implies false is false. False implies true is true, ex falso quod libet. And true implies true is certainly also true. So we have true, false, true, 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 false, true, true. Wonderfully, these two columns are equivalent. This is exactly the statement up here. This is the proof of such statements by way of writing down out in full the table, the truth table. Okay. So there are certain remarks in order. Remark 1. We agree on decreasing binding strength in the sequence decreasing. Okay, not is very strong, and is not so strong, or is even less. Then we have an implication arrow, and then we have an equivalence arrow. Okay, so if you have more symbols, you need to extend the sequence. However, the question is, how many operators do you actually need? Well, we had a few unary ones. We had a few binary ones. Well, what about higher order operators? Remark 2. Higher order operators, say the operator heart shape that eats P1 to Pn statements, so it would be an operator of order n. Well, unary operators are obviously of order 1, binary operators are of order 2. Higher order operators, heart shape, can be constructed, or I should say all higher order operators can be constructed from one single, well, not only higher, of any order n, from one single binary operator, and it's the so-called NAND operator, P, Q. I write down the table of the NAND operator, P. So let's have an up arrow for this guy. So true, 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 false, false, true, false, false, always the same order in case my writing gets worse. NAND is false, true, 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 because it's AND, but the negated version of it. It's NAND, not AND. And my statement is that any operator can be constructed from the NAND operator alone. So in fact, we do not really need this binding strength thing. It's just a convenience. All right, so I guess there will be some finger practice problems on the first problem sheet on that. Yes?
Just a short question. If you write down the equivalence operator in a table, such as this, is it only true when both sides are true or both sides are false, or what's the table for that one?
That's the definition of the equivalence operator. It's true if both propositions take the same value. Yeah. That's because on the other blackboard. Yes. Okay, further questions? All right. So this was a very quick recap of propositional logic, and we'll proceed to predicate logic. So section 1.2, predicate logic. Definition. A predicate is what one might informally describe as a proposition-valued function of some variable, or variables. Variable, because it could depend on several. So, for example, you could have a proposition P of x, and its truth value depends on what x is. True or false, dependent on x. You could have a predicate that depends on two variables, x and y, and now it's true or false dependent on what the combination of x and y is. Now, like in propositional logic, it was not the task to study complex propositions. It is, strictly speaking, not the task of predicate logic to tell you how these predicates are actually built. You might ask, okay, so what could this be? Could this be q of x and y is true if x is greater than y? So if x and y are numbers, say real numbers, and x is greater than y. That would be constructing such a predicate. Strictly speaking, it is not the task of propositional logic to construct them, because obviously in order to construct them you need some further language how you can combine objects x and y. That's the first thing. And then you might ask, well, what set do you take the x's from, and from what set do you take the x and the y from, and so on? And the answer is no such thing. we leave it entirely open what x and y, what they are, where they come from, what their nature is. They're just variables. They say this is very weird, because since elementary school days we've been conditioned to always say, what set does it come from? Now, the point is, we need to leave it this open in this fashion because we only want to define the notion of set later using this language, so we cannot already use sets. And in fact, it will be a part of set theory to introduce a fundamental predicate that takes two objects and makes out of these two objects a proposition that's either true or false. And you know this, the fundamental, so if we're not using this here, this comes later, so I write here later. We might define a fundamental predicate of two variables in this way using this element symbol. And you see now, if we already have a rough idea, but don't use this, just the outlook. If you already have a rough idea, x and y is, well, if they're sets, and that's actually the statement, if x and y are sets, then x element y is a predicate of two objects, which is either true or false. Okay? But this will come later, because so far, strictly speaking, in predicate logic of the first kind and so on, you do not have this symbol yet. So again, I cross this out because it's only later. At this level, we're only dealing with these predicates as the elementary objects. Okay? It's always important to know what a subject is not talking about. In this case, it's not talking about how to build these guys. Now, however, what we can do, we can again construct new predicates from old ones. Construct new predicates from given ones. And well, there is the simple way we could define a Q of x, y, and z to be, well, you see, instead of colon equal sign, which means defined as, because this whole thing for given x, y, z is a proposition, we can say it's defined to be equivalent to, say, p of x and r of y and z. Because obviously, if the x is supplied, if the y and the z are supplied, this is a proposition, this is a proposition, it's two propositions, they can be conjoined by the AND operator, and you have a new predicate now of three variables. Stuff like that, very simple. Now, a more interesting way is the following. You can actually convert a predicate of one variable into a proposition. Convert predicate of one variable, and this can of course be extended, into a proposition. So let's call this predicate P, capital P, of one variable. So let's write it down. Let's write down the proposition. Which proposition? The proposition is this. Funny upside down A, x colon P of x. So what is the proposition? Well, the proposition is all of this. So if you ask, what does this guy in the box mean? The answer is, it's a proposition. It's a proposition that has been constructed from a predicate of one variable, and we may read it, and that's the proposition. Well, we may read it more reasonably, for all x, p of x is true. So that is how we read this. For all x, p of x is true. But how is it defined? And this proposition is defined to be true, if p of x is true independent of x. independently of x. So if the x doesn't matter, you can substitute whatever you like for x, it's true. This is the definition of this proposition, and obviously this proposition has been constructed from this predicate. Now, I warned you, it's not our task here, in principle, to provide specific predicates. Nevertheless, as an example, as a feel-good example, we might do so nevertheless. So we could define a predicate. P of x is defined as, so now it becomes fishy, but that's the feel-good part. The feel-good always involves an amount of imprecision. X is a human being implies x, now let's be politically correct, x has been created. This includes all faiths, if you think God created it or the Father, whatever. But this is the whole statement, so the whole proposition. The whole proposition is this implication. Now, I said we don't want to say where the x's come from. Well, I don't. I just hide this in here. X is a human being, means x has been created in the mother's womb or wherever. Well, this is certainly always true. Then for all x, P of x is true. That's it. It's nothing more, nothing less. Yes?
So far you said we don't know anything about x, but if we would, could we also convert a predicate in other ways into a proposition, let's saying, okay, not for all x, but for some x?
Yes, indeed. Absolutely, thank you. That's what I was coming to next. There is the brother of this all quantor, so this is called the all quantor, and we can also define the existence quantification, that does the same, well, a similar thing. It takes a proposition of one variable, and now there is a different mumble jumble in front of it, which in total is a proposition, and this here we will read there exists an x such that P of x. This is how we read it, but how do we define it? Well, it's a proposition, so we need to provide the proposition that defines it, and that's simple because it's not all x not P of x. So obviously brackets like this, if you want them, we don't need them. Maybe we'll put a bracket around here for clarity. So having available the all quantor, you define the existence quantor as the negated all quantification of the negated predicate. Okay? And an immediate corollary from this is, well, it's really very trivial, is that for all x, something is not true, is equivalent to it's not true that there exists an x for which it is true. If something isn't true for any x, then certainly it's not true that there exists one where it's true. Very simple. It seems simple, and once it's written down, it's perfectly clear, and if you have mathematical training, it's clear. But if you go to the hairdresser from time to time, you see that in many German barber shops, on the door it says, what hairdressers can do, only hairdressers can do. It sounds good, but if you think about it, it means they can do nothing a non-hairdresser can do. So if I, as a non-hairdresser, can draw nice pictures, it means a hairdresser cannot. Okay, so careful with the negations and the all quantification. You quickly run into things you don't want to say. Are there questions so far? Okay, so a remark. The order, also, obviously we can use quantification also for predicates of more than one variable. Quantification for more, for predicates of more than one variable. For predicates of more than one variable. Right. So that looks like for all x, p of x and y, which is now a predicate of two variables. Well, what does this yield? Well, obviously, this yields a predicate of just one variable, namely the variable we didn't quantify over. So usually one refers to this as the bound variable. And to this y that survives the quantification and then appears again, we call this the free variable. And well, if you quantified once, you quantified one of the variables away, you have one variable left, you can quantify again. So that's remark 1. And the remark 2 is that the order matters. Remark 2, the order of quantification matters. So for all x, there exists a y such that p of x and y is generically different proposition than there exists a y such that for all x, p of x and y. And because the order matters, one should avoid, although it's very tricky to do so in the heat of calculation, but one should seriously avoid writing quantification after the expression. So very often we write this and that is true for all x, y, z. Or there exists a y such that this and this is true, and then we say for all x, y, z. Well, you should arrange all the quantification before the predicate, and then you have a clear idea of what the order is, because sometimes you write one behind if you formulate not so formally, and then sometimes one means you pull it to the front or you pull it here. You don't know. So it's best to stick to such an order. And you know this from, say, statements about inverse and neutral elements. No? So neutral elements for all x in the real numbers, there exists a real number 0 such that x plus 0 is x. But it's of this type to have the inverse element. No, that was just the wrong way around. I'm sorry. You see? Already mistake. Again, so for the neutral element, there exists a neutral element 0 such that for all elements, x plus 0 is x. Law of the neutral element of the additive neutral element of the real numbers. But for the inverse elements, for every x, you have a y. That means depending on what x is, you can choose your y differently. Something is true. Okay? So there you have an application of this. It's all very clear, but nevertheless, it's sometimes the root of some trouble. Okay? So, well, this actually concludes our quick overview of predicate logic. But there's an immediate application to all of this. This is our section 1.3, and that's called axiomatic systems. And theory of proofs. You all met proofs in your physics lectures, in the theoretical physics lectures mainly, in the mathematics lectures and so on. But what actually is a proof? Well, it's a way of arguing why something is true if something else that you assumed is true. But how do you argue? What are the valid rules of writing down a proof? Well, this can actually be defined. And there are some subtleties in this that actually render some of the proofs that are sometimes given, rarely, actually non-proofs. And if you are very serious about proving something, you need to know what the definition of a proof is. Well, we start with the definition of an axiomatic system. Definition. An axiomatic system. And you see, all this is preparation to write down the axiomatic system that defines set theory. An axiomatic system is a finite sequence of propositions A1, A2, ... to AN. Now, if one wants to be very smart about it, one could object here and say, what do you mean by finite? And what do you mean by numbers 1, 2, 3, 4, 5 to n? Because if you haven't defined sets yet, how on earth are you talking about numbers? Well, you could write this down as A1 slash, A2 slashes, A slash 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 slash. So logicians call these pre-mathematical numbers. It's what you do in Bavarian pubs. You have to. Okay. So again, if these lectures are attended by a mathematical logician, he will probably shout all the time, well, hang on a second, this is a little bit too naive. It's true. I'm not using the full first predicate logic approach to all this thing. It already showed up in my use of tables and so on. But it gives you the right ideas. It's conceptually exactly what they do without going into too much of the formal nitty-gritty, which for what we're going to do and what we're going to use it for would be fully redundant. Okay? So this is supposed to give you the right idea. It is the right idea. It's not necessarily what a professional mathematical logician would write down if he publishes his new research monograph. Okay? But this is putting the whole thing to classroom use. So this is my disclaimer. Doesn't mean that anything of this is wrong. It's all right. Okay, so an axiomatic system is a finite sequence of propositions. And these propositions are called axioms, which are called the axioms. Full stop. Definition. What is a proof? A proof of a proposition, let's call it small p, that's the thing we want to prove. A proof of a proposition within an axiomatic system So the idea is I first give you axioms, and then I set a homework problem, prove P, starting from the axioms. A proof of a proposition P within an axiomatic system, A1 to AN, is a sequence, and again is a finite sequence of propositions So informally we would say this finite sequence of propositions Q1 to Q capital M are the steps of the proof, if you wish, is a finite sequence of propositions Q1 to Qm, such that, now obviously we need conditions for this to be to constitute a proof, and the finite Qm proposition is supposed to be the thing you want to prove, the proposition you want to prove. Obviously, if you have a proof and you have steps, at the end, you better had the statement that you wanted to prove.
Does the proof always have to be a finite sequence?
Yes, yes, yes.
Because we know from physics and mathematics, for instance, we often use like convergence rules with like infinite series and.
Yes, but the individual steps. So actually, a finite sequence of propositions, I should add here, or propositional schemes. Now we're very clear. The point is, one single proposition in an axiomatic system can come in the form for all x, this and that is true. And then you can actually use the individual statements. If the proposition is for all x, p of x, that's just a proposition. But you can actually take the p of x out and say, well, this is for all x, then I can use p of x as an individual object, which is then true in maybe infinitely many instances, namely for all the x's that could be. And that we call a propositional scheme. So there is some subtlety there. But the actual steps of the proof must be a finite number of steps. It's very important. And when I was in my first semester, I had today I would say it was fortunate that my analysis professor was an intuitionist, so he didn't have proofs by contradiction. That was one thing. And the other thing is that he was sometimes really mad at some textbook proofs of analysis theorems. And he very often said, and this proof is not finite. And we didn't understand what he meant. Well, we now understand, because in the formal theory of proofs, you need a finite sequence of propositions. It's very important. Anyway, so it's such a sequence of steps, and they need to satisfy certain conditions. So proof is a finite sequence of propositions Q1 to Qn, such that condition A is satisfied, one of the following, such that one, such that for any j that lies between 1 and the final step, so that for any step of the proof, either of the following is true, either condition A is true, and that means that this jth step of the proof, that this qj is a proposition from the list of axioms. That means at an arbitrary step in your proof, you may pick one of the axioms and put it there. Very clear. You may put it there. T, tautology, or the jth step of the proof is a plain tautology, is a tautology. I think I didn't define formally what a tautology is. A tautology is a statement, is a proposition that is always true, independent of the elementary propositions it's made up of. So tautology e.g. P or not P. This is a proposition, right? And because P appears in there, and we don't know whether P is true or false, generically, we wouldn't know whether P or not P is true or false, because it could depend or would depend normally on P. But this specific combination, P or not P, well, this is always true, as you can check from the table. This is called a tautology. A tautology is a proposition that is always true, independent of the elementary propositions it's made of. And so either this, or for the jth step of the proof, the condition M is satisfied. So this stands for axiomatic, this stands for tautology, and this M stands for modus ponens, which is a very old logical, deduction rule. But we'll write it down here. I mean, there's nothing in the name, modus ponens, such that there exist M and N somewhere in the proof, that we had some, not somewhere, but actually before the current step. So if for every step it's true that, so we're in the jth step of the proof, we may use any of the previous steps, step M and step N, which are before the current step, such that there exist such guys, such that the proposition Qm and Qn, so you take the mth step of the proof, you take the nth step of the proof, you put an and between, implies the jth step, such that this is true. So please realize this is a proposition. Okay? So it could be that we have two steps before in the proof, and if I put them together by and I can show that from this and, implication arrow Qj is true for some m and some n before this jth step. If this whole thing is true, that also qualifies the jth step as a valid one. So the jth step can consist of an axiom, it can consist of a plain tautology, or it can be deduced from two previously arrived steps we arrived at, if this is true. Yes?
Do you really need the last one, or doesn't it follow out of A and T somehow? I mean, it's pretty much just an assembly of proportions, isn't it?
No.
Okay, that's probably...
No, you need it. You definitely, seriously, desperately, fully need it.
It's just probably somewhere which is so intuitively that you don't really see it.
Yes, because you have some kind of kindergarten intuition about this thing. You say, hey, if this is true, then I can do this. But remember, this is a binary operator. It's not more. It's not more. It has not this nice intuition about where the arrow goes, there the thought goes or something. It's just a binary operator. This is a logical statement. It's one of the axioms. At the moment, we don't have enough technology to provide a meaningful proof. But in this course, I will write out one proof in full according to this scheme, one single one. And that is, I think, the uniqueness of the empty set. Now, there will be an axiom that stipulates there exists an empty set with such and such properties, and then you have to show there's only one such set. And it's a very quick proof, and intuitively we say, yeah, it's clear, if you know the definition of the implication arrow. But if you really want to write it out, I think it has something like 16 lines. It's a 16-step proof if you write it out in full like this. And I want to present one proof that is precise. And the other proofs will be given in the form they're usually given, by some quick arguments. But the understanding of mathematicians is, well, yeah, I mean, even in the best journals, and the most celebrated theorems are usually not proven in this fashion, because this goes in the millions and billions, I don't know, of lines proving comparatively simple stuff. Okay, so we don't do that. We use like this is kind of like machine code in computer science, right? Almost like the zeros and the ones, the binary code, and actually the proofs we give in a higher language like C++ or so. Okay, so this is what we do in mathematics, but the understanding is that the proofs we write in books, we say, well, now it's obvious that da-da-da-da. The understanding is it's only a proof if your fellow mathematicians agree that in principle what was written down now could probably, according to our intuition, be broken down to proofs of this type. Okay? And if somebody has the feeling that what you do here will not lead to a proof of this type, for instance, not to a finite step proof, a proof with finitely many steps, then mathematicians will raise objection to this proof and will say, well, we're not convinced. And then in principle, as long as somebody says, I'm not convinced, a mathematician has to break down the proof more and more until you arrive here. So you can obstruct any lecture in mathematics. So it's, don't tell anyone. You can obstruct any lecture in mathematics by, you know, okay.
Doesn't it matter if here are some other propositions between M, N, and J?
No, it doesn't matter, because you can go back in your proof to an arbitrary point, because the rough idea is that everything there has been there anyway. It's an axiom or it's a tautology, and all the other stuff has been arrived at by implication arrows. That's the intuition. And so it suffices to look at stuff that was before, but because everything that comes after has been connected by an implication arrow. But you cannot go further than the current step, because that would imply that you used equivalence arrows. If you use equivalence arrows, you can go further down and say, oh, and later I show, so I can use it again now. Well, apart from some circularity, it's the directedness of this thing, very roughly speaking, intuitively speaking, that allows you to go to any previous pair of previous steps, even if there's something in between, but not further. Okay? Fine. Okay, so remark. If P can be proven from an axiomatic system A1 to AN, we often write A1 dot, 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 AN, and then this symbol means proves P. It's our short form for this. And of course, an obvious remark is that this definition of proof allows you to recognize a proof. This definition allows to easily recognize a proof. So in principle, you can give this a computer. You say, computer, please check, is the following a proof of this? That's very easy to check. An altogether different manner is to find a proof. Different matter is to find a proof for a certain proposition. And as you all know from your own experience, even set problems where usually if you're asked to prove something, it can be proven, this is not so easy. And sometimes it's so difficult that if you find a proof where people before didn't, you become a celebrated mathematician. So the theory of proofs here doesn't give you any hint of how to prove things better, but at least it tells you what you have written down right now, that is a proof. And that can be very useful, of course. Okay. A further remark is that obviously any tautology, should it occur in an axiomatic system or in the axioms. So if among the axioms there's a tautology, can be removed from the list of axioms without impairing the power of the axiomatic system. Well, that's very poetic. It means you can still prove the same stuff, because if you don't pull your proposition from your tautology from the list of axioms, you can put it anyway. So it's actually this axiom T that guarantees that. And an extreme case of this is, that's why I'm mentioning it, what is the axiomatic system for propositional logic?
Could you please write on the other table in the background, maybe?
Axiomatic system that describes propositional logic what is the list of axioms there? It's the empty sequence. Because in propositional logic, all we can prove are tautologies. Want to show something is true. Well, but then you don't need any axioms, because you can always pull a tautology into your proof by axiom T. Okay, I pushed this up for the camera. So this will become important in a second. But let's have one further definition. Namely, an axiomatic system is consistent. An axiomatic system is consistent, called consistent, if there exists a proposition Q which cannot be proven, from the or within the system of, from the axiomatic system, or from the axioms. Or to express this formally, not A1 to AN proves Q. There exists such a Q. Now, what's the idea behind this surprising, maybe, definition? Well, it's very simple. Yes?
I may be wrong, but I think I once heard that it's proven that it can't be proven that a system is consistent.
We'll come to that. My last statement of today's lecture will deal with that. Okay, so the idea behind the definition of consistent axiomatic systems is, imagine or consider an axiomatic system containing contradictory propositions. So for instance, A1, da, 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 whatever, yeah, pop, 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 pop. Then we have P, well, P, S as one of the propositions. And later on in the list, we have not S. Assume we have an axiomatic system that stipulates this. Then, by the deduction rule M, the one whose existence or justification was doubted, tentatively, then by M, clearly, yeah, I can pull the S into my proof. I can pull the not S into my proof by axiom A. And then I can use these two by M and connect them with an AND. And I only need to check whether for an arbitrary Q, this is always true. Is this a tautology? Yeah, this is a tautology. Because S and not S is always false, you remember? But if the assumption is always false, the implication arrow is defined such that the whole statement is always true. Ex falso quod libet. So it's again the definition of the implication arrow, which I dwelt on at the beginning so much, which shows that this is true, ex falso quod libet, whatever you like, well, whatever statement you like can be concluded. So by M, we can arrive at the truth of any statement Q. You can also arrive at the statement of not Q. It doesn't matter. So the problem is any statement can be proven if you have contradictory assumptions, contradictory axioms. Now, it's a sign of not having inconsistency, of not having contradictory axioms, if it's simply not true that every statement can be proven. But here, every statement can be proven. Hence, we need to exclude that every statement can be proven. This is just one example. This is the general definition of consistency. Well, having come this far, we can now write down an impressively sounding theorem, which is very trivial. Propositional logic is consistent. Propositional logic is consistent. That's reassuring. What's the proof? Well, we have to, it suffices to show that there exists a proposition that cannot be proven within propositional logic. That's clear. There's at least one that cannot be proven, then it's consistent. Now, propositional logic has an empty set, an empty sequence of axioms. You don't have any. So the only rules for a proof, only T and M must carry any proof. Now let's look at T and M again. The only only way by which you can introduce an entirely new step is by writing down a tautology. And then the modus ponens only allows you to take previous tautologies and to write down the QJ where all this thing is a tautology. So the only thing you can prove are tautologies. Only tautologies can be proven. But that means, that is, Q and not Q cannot be proven. Because not a tautology. So we constructed a proposition that cannot be proven. And so propositional logic is consistent. I mean, this is really trivial. Now again, an important remark is that while it's perfectly fine and clear how to define consistency, it's perfectly difficult to prove it for a given axiomatic system. Propositional logic being a big exception. But if the axiomatic system becomes more powerful, if you have more axioms like we're going to write down for set theory, you might then again ask the question, is this set of axioms consistent in this sense? And it's very difficult to prove that. And in fact, they're famously these statements first arrived at by Gödel that say to a certain extent it's even not possible to show this under certain circumstances. And I will give only a very rough taste of one of the things Gödel proved. So that's a theorem. It's Gödel. And it roughly, not being technical, goes as follows. Any axiomatic system that is powerful enough to encode the elementary arithmetic of natural numbers, which are the positive integers. So you see, I use imprecise language here. What's elementary arithmetic? Well, elementary arithmetic, it depends on what you need in a proof. It means you understand prime numbers, you understand products, stuff like that. Okay, rather elementary stuff, let's say elementary school mathematics. What exactly it is, one would see in the proof what you need. But any axiomatic system, it's powerful enough to encode the elementary arithmetic of natural numbers, is either inconsistent, never mind its successes with the arithmetic of the natural numbers, is either inconsistent or contains or contains a proposition that can neither be proven nor disproven. So variants on this formulation are, it contain true statements that cannot be proven. I mean, this sent shockwaves through the mathematics world at the time. What was this? Beginning of the 20th century, 20s, 30s, something like that. Because in mathematics, of all the arts, if you wish, the notion of truth seemed to be clear. Up to then, truth, or something was true if it could be proven based on a system of assumptions. So this was the pure truth of mathematics. But then Gödel came along and he, ironically, proved this and variants of this. Now, how does the proof proceed? Well, the proof is complicated. Or let's rather say the proof is involved. But the basic idea of the proof is the following. Assign, so first, assign to each mathematical or also meta-mathematical statement or proposition a number, the so-called, what later on people called, now called Gödel number. Well, a mathematical statement is a squared plus b squared equals c squared, something of this kind, yeah, for all tralala that exists, and so on. And Gödel, I mean, very roughly speaking, says the plus sign gets a number, the exponent gets a number, every variable gets a different number, the equal sign gets a different number. And then you can start talking about this equation. You can say the left-hand side of this equation has more symbols than the right-hand side. That would be a meta-mathematical statement, because obviously it's not a mathematical statement, it's a meta-mathematical statement. The left-hand side has more symbols than the right-hand side. But even to such statements, such meta-mathematical statements, Gödel would be able, or devised how to assign a number to even such a statement. You take primes, every elementary symbol is assigned a prime, and then you take powers of primes and you multiply the powers. You get big numbers. And then to meta-mathematical statements, you get a huge number. Boom, there it is, right? Now, you do this for just everything, okay? And then once you did that, in a sense, you have a number for everything. And because you have to multiply the numbers, you need elementary arithmetic. Now you understand why there's this mysterious condition on the axiomatic system that you're using being able to handle the elementary arithmetic, because this assignation of numbers and their calculation and so on requires this elementary arithmetic. And then what you do, you use the barber shaves all people in his village who do not shave themselves type argument to identify a proposition that is neither true nor false, neither provable nor disprovable. So you use some reflexive construction. You know this, I think, from the proof that there are overcountably many real numbers. You know that proof? You assume that you can write down every number, real number, in the form integer, decimal point, and then decimal places, d1, d2, d3, d4, da, 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 da. And then you assume that you can number every such expression. You assign a number to them. But then you actually use the number of the expression to construct a new expression, a new real number, which you can show is not in the previous list of numbers. It's kind of reflexive. You might want to revisit this proof. This is of a similar reflexive type. And here you do the thing, you assign to statements Gödel numbers, and then you produce a statement that uses the Gödel number of the very same statement. Okay? And then you arrive at such a contradiction. And as you can see, we defined axiomatic system. We defined what it is to be provable, and therefore what it means to be disprovable. That means if you can prove the opposite, if you can prove the negation. And we defined what is consistent. So according to our definitions, we fully understand this theorem. We understand the statement the theorem makes. The proof is a different matter. Okay, so at this place I will rest with the development of the language we're going to use to define axiomatic set theory, which that we will start next time. And we will start by looking at the element symbol, which is nothing but a predicate of two variables, because it takes a variable on the left, x, element y, a variable on the right, where it's just a matter of notation to write the symbol in the middle rather than writing element brackets x comma y. Okay, it's just notational convenience, and we very often do this for predicates of two variables, that we write the name of the predicate in the middle, because it just saves you two brackets and a comma. But this will be the elementary predicate of two variables, and there is no other in set theory. Even the equal sign between sets will be defined in terms of the element sign. And from this one elementary predicate of two variables, which will not be further explained, there will be nobody explaining to you in axiomatic set theory what it actually means that x is an element of y. And indeed, x and y will both be sets. So there is no such hierarchy like you are a set, a grown-up set, but you're only an element. No, no, no. Sets can be contained in sets. And a priori, one could even think about the question, is a set an element of itself? There's no a priori reason why you would exclude this. It would give you some kind of recursion. And you could ask, can you construct a set of all the sets that do not contain themselves? If you don't like these sets containing themselves, you could think, well, let's constrain the set universe to all those sets that do not contain themselves. And then you very quickly, actually in 2 lines, you prove that this construction, we'll do this next time, is not a set. The set, or let me call it the collection of all the sets that do not contain themselves, you only use this element predicate. This is no longer a set, as you can prove by asking the question whether that set contains itself or not, and that is neither provable nor disprovable. Well, both leads to a contradiction. So that immediately shows, okay, so the naive set theory is tricky, and we need a system of axioms that regulates our use of the element predicate. Okay? Because we know nothing of it. We just know there it is, and now the axioms give you rules of how to deal with it. It's a kind of an operational definition. Okay? You see if it behaves like this or if you use it like this, then you get what we can construct sets. There are some axioms that tell you these and those sets exist. For instance, there exists an empty set. Or if you have a set, there exists the power set of the set. That's the set of all the subsets of the set. You have to postulate this by axiom. And all the other sets we're actually going to construct from these previous sets. Well, in fact, you can show that the only set you really need to postulate is the empty set. So in principle, every set we're ever going to talk about is ultimately constructed from the empty set. The set that contains the empty set and the set with the element empty set, stuff like this. Okay? But there are actually, I think, 9 axioms. We'll see, depends on how you write them down, the number varies slightly. There are about 9 axioms that you can, or 8 I think I wrote down, that you can write down that regulate set theory and that reproduce the set theory on which all of modern mathematics is built. And occasionally, so you have an axiom that's called the axiom of choice, for instance, famously, or Zorn's lemma, some people call it, the axiom of choice. And you wonder, well, do you really want to have that, and why do we need to be so picky about the axioms of set theory? Well, for instance, if you do not postulate the axiom of choice, you cannot prove, that every vector space has a basis. Now, this we use very often. So you see, already in our building down there, where we're talking about sets, there are some screws you have to justify in order to have the whole building stand as we want it to stand. Okay? And there are other examples for that. So at least for completeness, and that's the purpose of today's lecture and of the next lecture, is to really look at the foundations of the subject, to have a good and justifiably good feeling about the further constructions that are to come. See you next time with axioms of set theory. Thank you.